approach is not the best, and there is something ingenious that gives us substantial gain. The question has both positive and negative sides. If you are able to solve something fast, of course it's good, but also if you are able to solve fast problems that appear in cryptography, that is usually considered to be bad because they will break crypto systems and so on. So it doesn't really matter which NP-hard problem to consider, but for some time in my talk I will concentrate on the satisfiability problem that surely everyone here knows about. But just to recall the definition, we have a set of clauses. The form that is the form is in conjunctive normal form. And we are to find a satisfying assignment, that is a truth assignment that makes every clause happy. Since we are interested in the true exponent, we will pay attention to not only to the base of this exponent, but also to the parameter. We can consider exponents in the number of variables, or in the number of clauses for such, or in the length of the input, or for some different natural parameter. And you can get different exponents. So what we are interested about? The trivial upper bound for satisfiability is just 2 to the n. That's clear. You just enumerate all possible solutions. Can we do it in still exponential but better time? Can we do it in sub-exponential time that will not contradict that p doesn't equal np? Or going to more practical questions, if we have a 1000 variable formula, can we solve it? Because, say, if you have a 1000 bit key, can an adversary break it? It doesn't really matter if the complexity is exponential. The question is, can we do it or not? And if the answer to some of these questions is negative, well, we can't prove it, because we are not able to prove even that p doesn't equal np. But can we provide some evidence for it, such as a completeness result, or some plausible assumption, some conjecture that will not be formulated just we can't solve a 1000 variable formula in one day. Something more structured.
I guess it still doesn't mean that even if you can't solve it, p could still equal np.
Yes, it can be equal or not. And still it's possible that we can solve it or we can't solve it. Okay, so what will be in this talk? Will be a little bit to talk about everything. So we start with algorithms for satisfiability to give the impression of how can we improve the brute force approach, to give an idea that it's not the only one. Then we come to lower bounds, essentially for the same algorithms that we will be talking in the first part. Then we come to structural questions that say about what happens if we can solve satisfiability in sub-exponential time. Can we, for example, then solve colorability in sub-exponential time? We will need some finer reductions than usual polynomial time reductions for that. Actually, we could be also interested in finer distinctions between the exponents, like if you have an exponent for 3 satisfiability, that is, each clause has at most 3 variables, and if you have 4 satisfiability, each clause has at most 4 variables. So if you have some specific exponent for one problem, which will be the exponent for another problem. There is research on this topic, but it will not be covered in this lecture. And then we come to the most interesting, to the most interesting questions, and also to the mostly uninvestigated questions. This is when it is important that something is hard, such as in cryptography or in de-randomization, which also will not be covered in this talk, but we will talk about cryptography a little bit. So we come to upper bounds. What is known for the satisfiability problem? Somehow the usual approach of divide and conquer, when we split a problem into several subproblems and solve each one separately, is called DPLL in this area, due to the papers of Davis, Putnam, Lodgman, and Lowland. So it's a simple divide and conquer approach. It already gives some improvement. But if one adds some global ideas to it, then the improvement becomes more substantial and the algorithms become much simpler. I mean global ideas about the search space. Maybe you don't have to explore some part of search space, or you can divide it in some smart way and employ some algebraic constructions and so on. And finally, we come to randomization of these ideas, which make these algorithms even simpler. So I feel they hide their philosophical contents. So what concerns divide and conquer? Okay, so what we have for a trivial brute force search algorithm? We have a formula, and we consider two cases when one variable is true and this variable is false. If one just use this approach, of course, he gets recurrency like that, and 2 to the n lives in this tree. We are interested to make the tree smaller. How to do it? Actually, when you substitute a variable by its truth value, of course, some parts of the formula can be simplified. Because if this variable is in disjunction with another variable, then also another occurrence disappears, and so on. One can add such simplification rules. One can consider many cases of what happens if we take this variable or this variable, what happens to other variables, and then we get better recurrences. This is a very technical work, and the last paper on 3 satisfiability that explored this approach had about 70 pages, and it was 1.5 to the exponent. After that, better, simpler algorithms came to the area, and people essentially stopped doing this mostly machine work, considering many cases. Though some people try to write programs for generating such proofs automatically. But so far for free satisfiability, humans are smarter than machines. So now we come to global ideas. The first global idea, due to Poturi, Kudlak, and Zane, from 1997 is as follows. Philosophical idea is that if you have many city-side assignments, probably your task is simpler, because you have to find just one, and there are many of them. And so let's consider the case when there is only one city-side assignment. This is not completely fair, but it can be proved that in the case you have many city-side assignments, this approach gives the same. So, for simplicity, let's have just one city-side assignment. Then, for each variable, there necessarily must be some critical clause. This is a clause that this variable makes true, I mean, in the city-side assignment. And this is exactly this variable which makes this clause true. All other values in this clause are false. Because if there is no such clause, you just flip the value of this variable and you get another satisfying assignment. We use here the uniquely satisfiability property. So, if we have such a clause, and if we already know the values for y and z, then we also get the value of x for free, because we just have a clause consisting of a single variable. So our task is to make a permutation of variables so that variables are the last in their critical clauses. Of course, we don't know which clauses are critical, because we don't know the satisfying assignment. But if we would take such a permutation at random, then naturally we would have about 1/3. And this also can be done deterministically, using an algebraic construction of group action, and also there are other approaches that are a little bit less efficient, but still you have a polynomial number of permutations. So if for ordinary DPLL you have more or less a typical tree with just two sums for each node, then here you first consider n cubed cases. These are different permutations, and after that you start a divide and conquer approach, because you have to find the values for these other variables in critical clauses for y and z in this example, and you have to find these values, but you will not need a tree of depth m. You will need a tree of smaller depths, like 2/3 of m. So smaller trees here. Smaller ordinary divide and conquer trees here.
No, but it's not clear. Why do we don't know which of these n over 3 clauses are really have the main variable, the last one? So
yes, we don't know, but we have some permutation, and we hope it is good.
Yeah.
If it's bad, we just will not get a satisfying assignment, because if we get an assignment, we always can verify where it's satisfying. So if the permutation is good, then we start assigning variables that are first in this permutation. Permutation gives us order, and we start with exploring the values of variables that are the first. Since we hope that permutation is good, then we hope that we will get many variables for free before we will try exploring their values. If y and z are the first in your permutation, then you have already considered their values, and in the right branch, where they are false, you already get x for free, and you forget about it. You will not need to split by x.
What was your definition of critical clause?
A clause is critical for variable x if in the satisfying assignment all other first x appears in this clause. Okay, this the definition that is written on the slide is for the case when x has value 1 in the satisfying assignment. So in this case, x must be present in this clause, and all other variables must be present with the signs that make them false in the satisfying assignment. So this clause is satisfied only because there is variable x there. Clear?
Yeah. So what you mean is that if you know that y and z are false, they don't necessarily need to be false, then you know x has to be 1.
Yes.
Yeah, but on some branches y and z are true still. There's not.
Yes, but
lead to a correct assignment.
These are just not interesting branches.
Maybe they are not interesting, but we have to investigate.
You will investigate them, yes. You will cut them at depth 2/3, and you will have n-cubed trees of depth 2/3.
Oh, so just I artificially stop at this, you mean?
At depth 2/3, yes. If you still have a non-trivial part in your formula after you assign 2/3, then
okay, I suppose somebody say Sasha should repeat the whole argument, because I guess that.
No, I didn't understand the complete. I can.
But then you just repeat the argument. What's the algorithm? So I assume that everybody has understood that what is a critical clause for a variable, right? Okay. Then starting from that point, just say it again.
Okay. The algorithm. First, hope that critical clauses. You have some ordering on your variables. So hope that for many critical clauses, the ordering is such that the main variable is the last in your ordering. So you will come to it
What
at
is
the
the
last
main
moment.
variable?
The main variable. You said that everyone understands what is a critical clause.
Yes,
a
but
clause
what's
is
the main
A
variable?
clause is not just critical, it's critical for a variable x.
Okay.
So x is the main variable. This is a variable that makes
X is the variable that makes the clause true.
Okay. Okay.
So hope that for many critical clauses the main variable is the last. Then start just ordinary divide and conquer. And when you get some value for free, just
Start, divide, and conquer for the first variable.
For the first variable in your permutation, yes. Then for the second variable in your permutation, then for the third, and so on, and cut it at depth 2/3. And if you get some variable for free, of course don't do divide and conquer on this variable, because you already know its value. So that.
So yes, the algorithm is supposed to be outlined. Right?
So what I did now, I understood it before. Not the permutation is made not inside each clause, but permutation is just the
For
whole
all variables.
entire list of variables, and then we can do. We go from the beginning to the end.
Yes.
We divide and conquer.
Yes. I'm
So
sorry,
how-
I didn't
have you
I
got the
didn't give
algorithm?
a further quotes.
No, it's very easy nowadays.
Yeah. Okay.
Take a random permutation.
But
right?
it says there's only n-cubed permutations. So apparently,
Take a random permutation for a subset of size n cube, which guarantees that for each subset of
subsize of that.
yeah. So you guarantee this with some technique which was not explained. So you are not.
Which will not be explained.
Yeah. So we are not assumed to understand this.
Okay. Okay.
But I can explain this technique for two. What? Oh. Well, for two satisfiability, because If you have just two variables in a clause,
You'd make this and that.
yes, you can just take one permutation 1 to the n and another permutation n to the 1. In one of them, you will definitely have half of.
Not the same without two clauses.
But for three clauses, it will be different. You will need the triple transitive action of.
But you say there is a small set of permutations. Which
Yes, yes. To get.
If I pick, from which one will satisfy that always.
Yes, there is a small n-cubed set of permutations, and one of them will be good. Yes.
And what is it?
I don't
Any triple transitive group of permutations with the sign solution.
Triple transitive action, because what actually triple transitivity gives you.
That's nice.
Okay. Let's continue.
Okay, so a different approach is to cover the search space by Hamming balls. That is balls in the Hamming distance. That is what is Hamming distance in the case of assignments. It is the number of places where two assignments are different, the number of variables that have different values. So we cover the Boolean cube, that is this whole search space, by a certain amount of balls, and you explore each ball. Each ball is explored essentially using DPLL, and why it works? Of course it works because we covered the whole search space and we explored each ball. But if we would just say so, then it's not clear why we get any gain, why we didn't search everything. Of course, we skipped some parts of search space so that our upper bound is better. I will better explain this on again on an example of just two balls. Normally we cover the search space using an exponential number of balls, and the whole tree of the algorithm looks again like that, but just the first splitting into many branches is not for n-cubed branches as before, but it's for some exponential number of branches. That's exponential number of balls, and then a small tree inside each ball. But let me explain it for just two balls. One ball is centered at 0, all values are 0, and another ball is centered at 1, all variables are 1. Now you need to here you need to explore assignments with at most half ones, and here you need to explore assignments with at most half zeros. How you do that? You look at some unsatisfied clause. Now, if a clause is satisfied, then nothing is to be done, everything is fine. So you look at some unsatisfied clause, say x, y, or z. Something is wrong with it, because it's not satisfied. So if you choose the correct variable and you flip its value, you will get closer to the satisfying assignment in the Hamming distance. So either you change the value of x, so now x is 1, or you change the value of y, or you change the value of z. Why I said DPLL? DPLL looked a little bit different like that. I said so because, first, if you decided to flip the value of x, you can now substitute it into a formula. And if you didn't, then you can assume that x will be kept 0. That is actually the assignment here will be x0, y1. And here the assignment will be like that. We could also live without it, without these zeros, and we will still get a decent upper bound. But I just want to emphasize that there is DPLL inside of all these algorithms. So, what is the depth of this tree? It is half of m. Half of m. And how many trees do you have? Just 2. So, what is the upper bound given by this algorithm? If it is 3 satisfiability, then you have just 3 branches, and in the worst case, you have 3 to the n half. But this is by far not the best covering. The best covering has an exponential number of balls, and we have to say how to construct, but this is beyond the scope of this talk.
But it depends also on the size of the ball, I guess. These balls are very large.
Yes, and if you have exponentially many balls, you can make them smaller.
Smaller.
So you need, this is called a covering code. This is a counterpart of error correction codes.
But how do you choose the covering code? Because it is not easy to find it.
Yes, but, well, I will say, but I will not write anything, because that would take us too far. There are two, first, if you choose a random code, it is good covering code, a random code of a certain radius.
Okay.
But we want to go deterministic. And then we choose a code for, say, 1000 variables that can be searched, it's a constant.
By hand?
Yes, okay. By hand, by someone else's hands. And after that, you can take a direct product of many.
I see.
Or you can also search for it using a greedy approach. That is also possible.
How can you search for it?
Huh? Okay.
With exponentially many things.
Now, greedy is not good because you need to look over all the balls in the greedy algorithm.
There are too many balls.
Well,
Yeah.
we can talk about it later.
Okay.
It is possible.
Okay.
Okay, so we come to randomization of possible approaches. Huh?
So I was wondering where showing.
Yes. Actually, randomized algorithms came before deterministic algorithms, and randomized algorithms are simpler. But I started the talk with deterministic algorithms to emphasize that actually there is DPLL inside of all these deterministic and randomized algorithms.
But was it also not Schoening who came up with the deterministic algorithm?
The term deterministic algorithm was an 8th-authored paper,
Okay.
which was a merge of 3 papers
Okay.
that were written at exactly the same time.
Because I thought this main idea was always Schoening's.
Yes,
Yes.
Explain it to me. And then.
He did. As far as I understand, when Schoening's thought about his random walk algorithm, he didn't know how to construct the code.
Exactly, he said, yeah, I remember, he said that he had
And so soon after his paper, several people in different parts of the world came out with how to do it, and Schoening with Gertz as well, and that was exactly at the same time. Our files were compiled within 36 hours from each other, so that goes fast. Okay, so randomized algorithms are actually simpler and their analysis is simpler. And for critical clauses, it's clear what can be randomized. You take a permutation at random, and you take random values for variables instead of considering 2 values for each variable. For the covering algorithm, you can take a random ball that is a random center of the ball and make a random wall. So that was the original idea of
Does it mean
the
that-
original paper. Sure.
Does it mean that in your tree you choose a random age?
Not exactly, because you also can somehow change the value of x backwards.
Ah, I see.
If you get to some other clause.
I see.
But why random walk helps? Because we just, if you what you mean by random walk, we just take make a random change or what?
In a random walk, you look at unsatisfied clause like that. And if it is unsatisfied, you choose one variable at random and flip its value. And why it works, it's a nice example by Dimitrov that if you do it for two satisfiability, then you have here a probability 1/2 of going in the right direction. And that means you have, if you consider the distance to satisfy an assignment, you have a random walk on a line. And the probability of going in the direction of the satisfying assignment is 1/2. The probability of going in the opposite direction is 1/2. And you have mirror here, and you have satisfying assignment in another corner, and that converges in n squared. For two sides, it's n squared. For three sides, the probability